right. Are you excited? So welcome to the last lecture of Physics 112. So you're almost done with me. And hopefully this class will help you learn about that physics is useful and many other things. So this is the last class. So and it will be a little bit less or a lot less rigorous than usual lecture. And if you want to finish early, we can finish early. It's fine by me. You should be upset if we finish early because we will not refund part of your tuition. You get less. Okay. So what do we learn? What have you learned from this class other than, you know, other than what? What anyone wants to share? This class is very informal. Yeah, Nathan. Cool. Anyone else? For right-hand rules. So one thing that many, I guess by now you probably are tired about this with this advice. When a student asks me what classes that they should take, you can ask me the same question also. Don't worry, I'm not gonna say take my next class because I know that you like me. Typically, I say take something that is interesting, that you're just curious. Like a good candidate probably 5 years ago or even right now is machine learning. You may not be a CS major, but it's always good to know more about machine learning. Or I don't know, poetry, Spanish literature, anything. But I wish I took machine learning when I was in grad school. Part of it is, so I just got back from a conference. I got back at my house at 2:15 a.m. this morning. And because I have son, I was happy to inform you that I woke up at 6, so less than almost like 2 hours of sleep. And that's part of it because of familiar responsibility. So if there is one thing that you can take from this class, is that being a father is awesome. It's probably the most important job. My first job is being a husband and father. That's if you want to take one thing out of this class. And if I make fun of my wife, it's because maybe my family is dysfunctional. That's how we interact at home. So other than that, yeah, I went to a conference and I talked to some graduating PhDs and I asked them like, what is the best advice that you took when you were a grad student? And that's, I think, consistent throughout impressive graduate students that I talked to. Because I also met half decent graduate students or graduating graduate students, but the impressive ones, they took, let's say, machine learning 5 years ago, before ChatGPT exploded. Okay. Anything else? All right. So next is let's talk about your grade, your favorite topic. Yeah. So this is actually not the latest version of the syllabus. So if you go to Canvas, the syllabus, when I say the syllabus, I need to be careful. So if you download it's right there, the lectures, all lectures, it now has the latest syllabus. So, sorry, not this one. But basically, the sentence here, so I didn't realize until somebody mentioned this in the email. It is a typo. Maybe I was like under 2 hours of sleep also at that time. This one is not correct. So for exam, the lowest grade will be dropped. And let's see. So the lowest grade will be dropped. and then this one is still correct. So you can use the average of your best 3 exams for your final exam. Is that clear? Are you sure? I wish I can share you my inbox. I get many emails, and it has been fun answering those emails. Any other question about logistics? Final exam will be on Canvas. It will be because as you schedule it on my behalf or on everyone's behalf, every teacher's behalf, it will start at 9:40. I don't have option, so 9:40 a.m. until, so you will have 2 hours for that. So this is the latest syllabus. Interesting. Yeah. So lowest grade will be replaced by the final exam score. Wait, no, this is not the latest syllabus. Oh, apologize. Sorry. So that's the one that I uploaded to Canvas. I need to check before. Yeah. Anyway, I'll make sure. But basically, you can the lowest grade of your exam will be dropped, and it's recorded, so you can use it against me if I made a mistake. Okay. Should we finish quantum mechanics? Good. So basically, I have one theme in the class is that physicists come up with because the beauty of science is that we keep on making discoveries. That's why I still have a job. So if one day maybe physicists will figure out everything, we come up with theory of everything, then at that point I can just put all of my stuff in my office in boxes and do something useful, like fixing, I don't know, fixing elevator. Let's say. Okay, so in physics we built a new theory. What makes us construct new theory? What kind of event? What kind of thing that lead us to make new theory? Like, yeah, new observation. Typically, somebody do something that everyone ignores. One example is that we know that if we have positive and negative charge, there is Coulombic attraction. And people knew that, but turns out that in wires with flowing electron, it also generate a magnetic field. Right? So this is one example. The one that we discussed, I think on Wednesday, was if an object move at slow speed, then we use Newtonian mechanics. But if the object, if v here is approaching the speed of light, then we use what? Special relativity. Okay. And similarly with quantum mechanics, if the object is small, then we use quantum mechanics. If the object is big, like our galaxy, our universe, we use general relativity. Okay. So let's finish quantum mechanics. So basically, quantum mechanics, what we learned last time is that, one thing, just in case you miss Wednesday lecture, this material will not be on the final exam. So you can just relax. Okay. So basically, one of the reasons why we study interference, other than, let's say, if you want to understand why your glasses look a little bit greenish, or why soap bubble has a lot of color, is that it played a central role in the development of quantum mechanics. So last time what we did is we use source And this source is a weak source of light, and we expose it to two openings, slit 1 and slit 2. And you put screen here. Basically, what you see is interference pattern. Okay. In the first, I don't know, 1 hour of the experiment, you see localized spots, which is meaningful. Localized spot means localized position, energy, and momentum. That means light has a particle-like characteristic. Okay. But if we run it for, let's say, overnight, over the weekend, we see it depends on the number of photons that you generate. We start seeing interference pattern. Okay. So that's consistent with what we learned before, that light is an electromagnetic wave. Okay. So we study that. And then I really like this. This is actually a special relativity of, sorry. This is a special relativity formula, but basically, if we play with math, the number only makes sense if the mass here is equal to 0. So this is why initially people conjecture, and I think right now it's still a conjecture, meaning we don't have proof that the mass of a photon is 0. But based on many equations, we know that the mass of the photons, if I said electron, apologize, photon is equal to 0. Right. So this is kind of summarize what we learn, what we know. Basically, we go back and forth between particles and waves. Light, the name is dualism of light. Light is light is both particles and waves. So when we talk about particles, we talk about position, energy, and momentum. And wave, we talk about frequency, wave number, interference, diffraction. Okay. So that's the summary of Wednesday lecture. But you know, graduate students need to graduate. So there is another experiment that people do. So instead of using lights, they use electron source. Okay. And maybe I need to highlight this weak source of electron. So when they ran the experiment, they saw similar thing, meaning initially one electron either, so it turns out that electron either choose slit 1 or opening 2. Maybe this is the first one, the second one, the third one, the fourth, the fifth, something like that, something like this, basically. And then if this graduate student ran the experiments for a long time, they also see interference pattern. Okay. So why is this meaningful? Why seeing position of many electrons is meaningful? Yeah, you're at the back. I haven't called you. Yeah, you. Yeah. Just guess why this is interesting. Why seeing this interference pattern is interesting. So electrons is a basic, you can call it unit of particle, right? And particle, typically we don't think particle can generate interference. So the fact that electrons can generate interference pattern, that means electrons also behave like waves. So not only photons behave like particle and wave at the same time, turns out that all of us behave like particle and wave at the same time. The reason why we don't see it, because we are big, not as small as electron. It has something to do with the wavelength. Your wavelength, the wavelength of this paper towel is very, very small. but the wavelength of a single electron with momentum p is noticeable, meaning the wavelength is on the order of this separation here. Okay, so that thing is interesting. And then typically when we model a wave, we use what kind of function? Meaning like if we in this class, if we describe a wave, what kind of trigonometric function that we use? Tangent, cosine, sine or cosine. That's what we will use for the rest of the class. Any questions so far? You? No, yeah, you with white shirt. Yeah, what's your name? Ashwin? Ah, okay. Interesting. My best friend's name is Ashwin. He's an MIT professor. No, I asked you whether you have a question. That's the question. Oh, okay, good. So everything is clear. I know that my lecture is clear. I've seen your end of class videos, and I need to comment those. But with a weak internet connection, it was difficult to handle Canvas. Yeah, Arman. Ah, so how did we derive that? It's a function of Poynting vector. So mass, we know, so in physics, there are laws. You know, it's a mathematical term. It's also a physics term. Laws like Newton's laws, you cannot derive that. It's something that is based on measurement. So the fact that maybe you think that I'm not answering your question, but this is one way to say it. The fact that we see individual spot here, that means it has energy and momentum. It's like when somebody punched me here, you will see a spot here. That means that fist has energy and momentum. And then because of its, okay, what is this spot? So this black surface here is a film. And when a particle hit a film, it makes a spot. And the fact that what we see for a single electron is individual spot, that means it's a particle because it has localized energy and position. Sophia. Yeah, I think maybe if you ask Ross, he has a better answer. I'm just a little like a goofy biophysicist. Yeah. Photon doesn't have mass. Yeah, electron has mass. Proton has mass. Any other question? Excellent. You guys still engage. So it's a wave, and wave has energy. It relates to Poynting vector, and it also has a wavelength. If you are curious, the graduate student who get Nobel Prize for his PhD thesis, the name is, oh my God, I Google how to pronounce his name, but the Broglie, I think. My wife speaks French, I thought. So the Broglie wavelength is so basically P is equal to hc over lambda. Wait, so this is energy. Sorry. It's here, sorry. Energy is h bar over omega. But for this class, let's just do h over frequency. If you read other books, the symbol for frequency for quantum mechanics is actually nu. But I think in these notes, I use different notations. Okay. Yeah, this guy here. So there is this formula derived, or it was a conjecture by de Broglie. So yeah, lambda is actually here. H over lambda. Okay. The reason why it looks different because H bar is H divided by 2 pi. So H is equal to, and for this lecture, all you need to know is that H is a small number. Because if H is big, then it will manifest in our daily life. The name is Planck's constant. Anyway, any other question? If it doesn't make sense, because it's because quantum mechanics is strange. Okay, so I don't expect this to make sense. Even Feynman said that quantum mechanics doesn't make sense. Not because he doesn't understand it, it's because it's just strange. I mean, who are we to expect electrons to behave the same way we do? We are not their boss. Any other question? Nick, do you have a question? Okay. All right. So, and then there are few important experiments, and I'm just going to mention it briefly. One is photoelectric effect. It's an important experiment. This is what gives Einstein his Nobel Prize, not the theory of special relativity, not his theory of Brownian motion. Those are very fundamental, very important in nature. One is photoelectric effect. Basically, all you need, well, not all you need, is actually a really tedious and clean experiment. You need a clean metallic surface, so it has to be pure. And then what people did, they hit it with lights at certain wavelength, okay? Any question? It's really simple. So one thing, certain wavelength, so this is basically hc divided by lambda. So the shorter the wavelength, the higher the energy. So this is the experiment. Basically, metallic surface has many shared electrons, and people hit it with photons with a given wavelength. And there is a detector here that will capture ejected electron from the metallic surface. So this, sometimes when you read scientific papers, you wonder, why people study fruit fly, or why scientists study, I don't know, DNA that can detect target. But sometimes, if you're lucky, that's how we better understand nature. So this experiment is really important. It turns out that there is a cutoff wavelength. So omega. Let me. This one is basically has something to do with 1 over wavelength. Okay. So 2 pi f is equal to omega. And then this is why I switched the axis from h omega, so h bar omega, in case you're curious. So, and then this one is proportional to 1 over lambda. So it turns out that if the wavelength is too long, then you cannot eject electron. But if the wavelength is longer than, no, shorter than this threshold, you can eject electron. Why this is interesting? Amanda. So, and it doesn't have anything to do with how fast you hit the surface. So if photon is a particle, then you would think that the wavelength doesn't matter. You just hit it with really fast flux, or just hit it for like days. you will make a dent. You will somehow eject this electron. But turns out that what matters is the wavelength of the electron. Okay. So that means electron is, what do you associate wavelength with? With a wave. And this is interesting. I think the analogy that I wrote on the lecture, it's like, yeah, it has to be the energy, or the photon needs to have certain energy to eject electron. And the mechanical analogy is like, I can lift this device easily, but let's say let's say you bring, I don't know, 1,000 babies. This thing, they will not be able to lift this device, despite you have like many babies here. I don't know whether that makes sense or not. Okay, good. Any question? We're going really fast here, I apologize, but I want to leave you with some appreciation or some knowledge of quantum mechanics. So going to school is like climbing a mountain, right? It's difficult. I understand. All of you are under a lot of pressure, and physics can be difficult, biochemistry can be difficult. But once you reach the top of the mountain, you have amazing views. You can see it, you can appreciate it, you can meditate, and then after that, you just go downhill, like really easy. So this is what we are doing right now. If it's difficult, because that's how we learn new things. All right, next. Hopefully that's my last pep talk of the semester. So next is Compton scattering. So Compton, what is his name? I don't remember his first name. So Compton is, there are many people that are very fortunate. They were raised in academic family, and Compton is one of them. Lawrence and Harry Bragg, we discussed X-ray diffraction and mentioned their names. My PhD advisor is one of them. He said that 60% of his uncles and aunts are professors. His sister is a professor. He's a MacArthur Fellow. His PhD advisor is MacArthur Fellow. His postdoc is MacArthur Fellow, and so many MacArthur Fellows in his circle. So Compton is one of them. He is, of course, because this experiment is being discussed in many universities in different continents right now, he, of course, received Nobel Prize. His brother, another Compton, is, two of his brothers are university presidents. One of them was the president of MIT. The other one is also a university of really awesome university that is near and dear to my heart. Any guess? Huh? No, not Caltech. I was trained not at Caltech. No, I was mostly trained in Michigan, but I love Caltech. It's very near and dear to my heart. Not ASU. ASU is also near and dear to my heart. I don't deserve this job, but Compton is he's the president of Wazoo. So if you go to Pullman, our Memorial Union, we call that building Compton building. Anyway, this is the guy that got Nobel Prize. Maybe you can probably see that he is probably more determined than his brothers. All right, so basically this experiment, so instead of quizzing you, I will just tell you that it turns out that if you hit electron at rest with lights, the incoming lights got deflected. Okay, so even if we instead of drawing light as a particle, if we draw it as a wave, it got deflected by an angle, and also the wavelength changes. So it lost energy and also changed its momentum, meaning like the direction. So, and then people, of course, did mathematical derivation of scattering process. If you are interested, you can take both classical and quantum mechanics courses at ASU, and you will learn the math. But basically, this experiment by Compton show that light is a particle. So I show you one example, one experiment, one classic experiment that shows light is a wave, which is photoelectric effect. It led to a Nobel Prize award to Albert Einstein. The second one is Compton scattering that shows light is a particle. Any question? Good. All right, so now let's do something. Let's do quantum mechanics, like the real quantum mechanics. Okay, so the summary right now, that everything, including yourself, can be described by wave and particle. But the smaller the particle, the wave component gets easier to observe because the wavelength is observable. You can use this. Anyway, this is about on the order of, as far as I remember, 10 to the minus 34th, right? So, sorry. So let's say if you want to do lambda, your lambda of a human is equal to h divided by p, right? If the Planck constant itself is on the order of 10 to the minus 34th, and let's say our momentum is 1 kilogram meter per second, then the wavelength will be 10 to the minus 34th, which we cannot measure. But for an electron, the momentum is small enough, and we can easily see the wavelength of an electron. And then we have covered two-slit interference with light, with a feeble source of light and electron. So next, what I'm gonna briefly show you is that if we take this postulate is something that you don't prove. It's something that initially start as a mathematical construct. It's like a projection or like a I don't know whether this language is familiar to you. In math, there is law, conjecture, proof. It's something that we don't derive, something that you come up with when you build a construct. All right, so light is a wave, so we have and a particle. So we have wave, lambda, and k. K is lambda and frequency, and k is 2 pi divided by lambda. Omega is 2 pi f. Okay, and one way to describe light is we draw it as a wave. It turns out that it has a meaning, right? So it turns out that the intensity of the wave tell us the probability to see the electron. Okay. So if this is, and I'm gonna use this funny symbol psi, which turns out this is not a sun devil. This is a psi. Turns out that it's not a funny symbol. This is a quantum mechanics symbol. Then the probability is just the square of psi. For now, it's not that important. So this one is interesting. Let's just square it. That means this is the probability. And the probability has to be normalized, meaning the sum of all probability has to be equal to 1. Because if you sum all probability, it has to be 1. That means at any given point of time, the electrons, like not a given electron is in many different positions at once. Okay, does it make sense? Is that good? So So this is my probability. Okay, this is my house, and I built my house in front of my mosque. So this is my mosque, and this is a road between my house and office, and this is this classroom. So this is my probability. Something like this. Well, I work quite a bit, so like this, right? But you know that at a given point of time, I will be either in my house, in my mosque, on the road, in my office, or here. Unless I get hit by a truck, then maybe here and here. But electrons actually at any given of time, they're all in this position. And when we make measurement, like hitting electron with a screen, then everything collapses into one position. But before you hit it with a screen, it's everywhere. So that's what led Feynman to think that quantum mechanics is strange. So our universe is big. So instead of solving the problem in the universe, like using universe as a system, this is something that very few textbooks use. I think I only saw in one textbook. We will study in the context of a circle, and you can view the circle as the orbit of electrons, an electron around a proton. Okay. So electron either go clockwise or counterclockwise. So instead of having like infinite plot, we can just do plot from 0 to basically around the circle. Can be, I don't know, 0 to 2 pi r. Okay, that makes the math easy. Okay, so that's one thing. So another thing that I'm gonna invoke, if you want me to slow down, you can just tell me to slow down. I'm trying to finish everything in 12 minutes. Okay. So if this is the orbit of an electron, because we use wave to describe the behavior of electron, then I don't know how to draw it, but basically the wave travel around the orbit. Okay. It's actually a poor 3D drawing on my part. So so it goes like this. So if we have a circle here, it goes up and down. This is the probability to find the electron. So it turns out that there are many solutions that satisfy that requirement. So you have this, you can also have the same orbit, but with longer wavelength. One thing that needs to be true is that it needs to have a single value, because you cannot have multiple. It's a single particle. So you at this coordinate, I don't know, 1, let's say. It needs to have 1 values. Okay. That means the diameter needs to be integer times wavelength. Okay. Does it make sense? The wavelength either, sorry. Divided by wavelength. Okay. And I probably miss a factor of 1 half here and there. But basically, it can be we can have multiple solutions, but they are discrete, meaning the solution is not continuous. The wavelength has to be either lambda or lambda divided by 2, lambda divided by 3. Is it clear? This is actually very important. If I'm a big fan of tattoo, we should go to a tattoo parlor and have tattoo here, because it's very important. This is how quantum mechanics get its name, because the solution is quantized. So we should, like April 26, 10:51 a.m. That's when we learn about quantum mechanics. It's a big moment of your life that you should remember. 20 years from now, if I go to your practice, you can like, yeah, I still remember. April 26th. Awesome. So that's how quantum mechanics gets its name, because the solution is quantized. So P is h divided by lambda. Unfortunately, there is L here. L is perhaps 2 pi r. But you can have different wavelengths, but turns out that n doesn't have to be positive. It can be negative. That means that the particle either go clockwise or counterclockwise. So there are multiple states. An electron, any electron is in combination of states, not just electron doesn't pick one until you make measurement. Electron is in all states, and every state has, for this model, has two substates, which is clockwise and counterclockwise. And some of you are expert in spectroscopy. There is a way to detect all of this energy state now. Okay. So this is just one. So P, you can derive it yourself. P, it turns out equal to 2 pi times n. So this 3 here is n. And the reason why the bottom one is -3, because here we insist that n is equal to -3. And we know that energy is P squared divided by 2m. Do you know this or no? P is mv. P squared is m squared times v squared divided by 2m is, so we get 1/2 mv squared. Okay. So the energy is basically proportional to n squared. Okay. And since electron in this simplest model can be in many states, the energy is proportional to n squared. So these are the energy level that you can see, that you can detect using spectroscopy. And each energy level have two that you can split, let's say using magnetic split. The name is, I think, Zeeman effect. So when you do spectroscopy, you see multiple peaks of a given state. It's because one state can have two substates. There could be more than two, can be triplet, doublet, quadruplet. Okay. And then when an electron transition from, let's say, excited state to lower state or to ground state, it emits wavelength. And you learn this in your chemistry class, is that right? So the wavelength is basically proportional to the difference in the energy. And since energy is a function of n squared, so let's say the transition from 2 to 1, then the energy difference is 2 squared minus 1 squared times all this constant, basically times P, I don't know. The thing is P divided by n. Anyway, this is a constant, and this ratio is a function of n. I just realized, any questions so far? This is actually kind of important, the last important point perhaps. I just realized that I haven't given you iClicker point since I promised this morning. Maybe let's just do one iClicker question. The question is simple. One is yes. No, A is yes, B is no. The question is, are you planning to take final exam? And there is no correct answer here. Even if all of you say no, I will still prepare final exam. Right? So it's on iClicker. And it's not you don't have to promise that you will take or not take the final exam. It's just to give you points. The final thing that I'm gonna say is, it turns out that you can do the same quantum mechanics for many, many, many things. One example is this polymer, let's say, and it doesn't have to be this polyacetylene, can be any polymer. Turns out that this one behave like if we have electron will be localized along the contour of this polymer, and there is a model system in physics. The name of that model system is particle in a box. So maybe in the future, if you read particle in a box, it's basically a one-dimensional model of a particle that is confined between 0 and L, basically a box. The particle can be anywhere in the middle, but not outside. Okay. Basically, at this point, the potential is infinity and potential is 0 in the middle. So potential here is infinity and 0 along the protein, along the polymer. And the thing is, if you come up with a solution for that problem, the probability will vanish at the end of the protein, and it should be larger in the middle of the polymer or particle in a box. So this is the one solution. N is equal to 2 is a different solution, and 3, n is equal to 3 is a different solution. A different solution means that the wave has a different psi. The Greek symbol that looks like SU fork. Okay, and because they have different frequency and wave number, they have different wave number, they have different energy, and it looks like this. Okay. Any question? So basically, probably this is the last point that I want to say, that I want to convey to you, which is electrons, they don't have to obey the same laws that we follow. They can be in many, many states. They can be in the ground state, first excited state, second excited state with given probability. And we found the probability by squaring the wave function. We call this psi a wave function. So that's quantum mechanics. So maybe we can review the class. Sorry, we don't have time to review. Just joking. Because I cannot review like 4 midterms in 2 minutes. But we started the class with what? With a demo of fluctuation or Brownian motion. Basically, at higher temperature, things jiggle faster than at low temperature. And then we end with quantum mechanics. I guess that's the easiest way to summarize the class. So we still have 1 minute. Maybe typically I say thank you. It has been an interesting class. You guys actually operate at much higher level than previous cohorts, but different classes have different character. So I've been challenged by you, but I really cherish the challenge, and I actually like teaching this cohort a lot, and I'm gonna miss it. And then if you need any letters or if you have any questions about physics, career, life science, you're welcome to stop by my office, email me. And if you see me outside the class, just say hi. All right, thank you, and I wish you the best in your career and have a nice summer. Yeah, good.